We're going to go ahead and continue with example 13.6. This example states, suppose your bicycle tire is fully inflated with an absolute pressure of 7 times 10 to the 5th pascals at a temperature of 18 degrees Celsius. What is the temperature after its temperature has risen? What is the pressure after the temperature has risen to 35 degrees Celsius? Assume that there are no leaks or changes in volume. Okay, so we just learned that the ideal gas law states pressure times volume equals N, the number of molecules, times K, the Boltzmann's constant, times temperature. Okay, and it states that there was no changes in volume. Okay, so what we're going to do is we're going to compare the ideal gas law equation before and after the temperature has risen. Okay, so what we'll say is that the pressure, the starting pressure times the volume, because the volume doesn't change, is equal to Nk times the initial temperature. Okay, and we'll take that and we will divide the final pressures and temperature equation. Okay, so we're going to take this one, the final, and divide it by our initial. Okay, so we're going to say PV equals NKT. So PV equals NKT. And we're going to divide that by our initial state. Okay, so you can notice that some things will cross out automatically. Our volume didn't change, so that crosses out. N and K are also going to remain constant. Okay, so then we get this equation, P over P naught equals T over T naught. Okay, and we're looking for the final pressure, so we can solve for that as so, and then plug in our numbers here. So our pressure is going to equal our starting pressure, which was 7.0 times 10 to the 5th pascals, times our ending temperature. And remember, these need to be in Kelvin. Okay, so what I'll do is I'll go ahead and convert that. So we have 35 degrees Celsius plus 273.15, and that's going to be in Kelvin. Okay, divided by 18 degrees Celsius plus 273.15 Kelvin. Okay, so once you solve for these and plug into your calculator, you'll get a pressure of 7.41 times 10 to the 5th pascals. Okay, so this is your final pressure of the bicycle tire. Okay, so let's go ahead and continue with our next example, 13.7. It states how many molecules are in a typical object, such as gas in a tire or water in a drink. We can use the ideal gas law to give us an idea of how large N typically is. Calculate the number of molecules in a cubic meter of gas at standard temperature and pressure, STP, which is defined to be 0 degrees Celsius and atmospheric pressure. Okay, so let's go ahead and first write down our ideal gas law, PV equals nRT, or NKT, sorry. Okay, And we want to know the number of molecules, so I'm going to go ahead and solve for that. So N equals PV over KT. Okay. It states we have 1 cubic meter of gas, so the volume is going to be 1 meter cubed. Our temperature is 0 degrees Celsius, which means 273 Kelvin. Okay. Atmospheric pressure, P, is either 1 atmosphere or 1.01 times 10 to the 5th pascals. Okay. So using all of that information, we can solve for our N, number of molecules. So plug in our values. Pressure times volume divided by K, which is 1.38 times 10 to the negative 23 joules per Kelvin, times our temperature. Okay. So once we plug that into our calculator, we get the number of molecules is 2.68 times 10 to the 25th molecules. Okay? Whoops. All right, so this is our number of molecules in a cubic meter of gas. Okay? Now let's talk about this idea of Avogadro's number and something called a mole. Okay? A mole, or MOL, as we can abbreviate it, is the amount of a substance that contains as many atoms or molecules as there are atoms in exactly 12 grams of carbon-12. Okay? And in this figure, it shows how big a mole is. Okay, and this is on a macroscopic level, so typically we're looking at this in microscopic levels, not macroscopic levels. Okay, so we are kind of sizing it up to be the number of tennis balls. Okay, so for 1 mole of tennis balls, or table tennis balls I should say, would cover the Earth to a depth of about 40 kilometers. Okay, so it would cover Earth over and over again at this depth of about 40 kilometers. Okay, and Avogadro's number is the actual number of atoms or molecules in 1 mole. Okay, and that value remains constant. It is 6.02 times 10 to the 23rd molecules per mole. Okay, so you can just state per mole, or you can say molecules per mole. Okay? All right. So using this information, we can go ahead and do another example, 13.8. It states, calculate the number of moles in 1 cubic meter of gas at standard temperature and pressure. Okay, and we did find the number of molecules, okay, in the last question, the last example. So I'm going to go ahead and use that information. So we said that in 1 meter cube of gas at standard temperature and pressure was 2.68 times 10 to the 25th molecules per mole. Okay? I'm sorry, not per mole. Molecules in meters cubed, in 1 meter cubed. Okay? So if we want to know the number of moles, okay, per meter cubed, we would take that value molecule per meter cubed and divide it by Avogadro's number, 6.02 times 10 to the 23rd molecules per mole. And once we divide that, we get a value of 44.5. And this now will be in moles per meter cubed. Okay. So again, to find the number of moles in 1 meter cube of gas, this is how we would find it. We take our value that we just found, or N, and plug that in, divide it by Avogadro's number, and we get our value. Okay? Then we can convert this to the number of liters of gas per mole. Okay? So there are 10 to the third liters of gas per meter cubed. Okay? And we take that and divide it by our N, or 44.5 mole per meters cubed. And we get a value of 22.5 liters per mole. Okay? Alright, so this is a lot of conversions. Now, we can also define the ideal gas law in terms of moles. So we don't have to go in terms of molecules. We can also go in terms of moles. And that is going to be pressure times volume equals N times R times T. Now, what is this R? R is equal to Avogadro's number times the Boltzmann's constant, K. Okay? And there's a few different ways that we can write it, depending on what values we are given. Okay? So a lot of times we'll use this first one since it's given in joules per mole kelvins. Okay, joules is energy, right? So typically we will use this one, but it may come up that we need to use one of these other two. Okay? So we can look at an example of this. Example 13.9 states how many moles of gas are in a bike tire with a volume of 2 times 10 to the negative 3 meters cubed, or 2 liters, a pressure of 7 times 10 to the 5th pascals, and with a temperature of 18 degrees Celsius. So we just found PV equals nRT. Okay, we have R, we have temperature, volume, and pressure. So we're looking for N, our number of moles, so we can solve for that. Okay, and just plug in our values. So our pressure is our pressure is 7, looked at the wrong thing there, 0.0 times 10 to the 5th pascals. Our volume is 2.0 times 10 to the negative 3 meters cubed. R, we know, is 8.31, and the units are joules per mole times K. Okay. And our temperature is 18 degrees Celsius plus our conversion here. Okay. All right. Once we plug that into our calculator, we get our number of moles is 0.579 moles. Okay, and we'll go ahead and continue in the